In this lecture, we're going to be discussing RRT star, which is an optimal variant to rapidly exploring random trees. We're going to show two basic improvements that can be made to RRT to ensure that the planning asymptotically converges to the optimal result. So let's go ahead and get started. The first change we're going to make is known as this extend step. And I'm actually going to add notation to this and call this extend star. This goes with the literature on RRT star. Because RRT arguably already extends the graph, and in RRT star we're going to do an optimal extension of the graph. Okay, so in RRT we've gone through and we're rapidly exploring the tree, right? And say we have a new sample. Say the new sample is right here, and so this is what we were calling P before. So we have this new sample P, and we'd typically say, all right, well, this node right here, that's the closest possible node. We extended a distance D, and we say, all right, well, that's going to be the node. And if that were it, we wouldn't have anything else. We'd say, all right, we're going to add in this new node to the previous tree, right? But if we start to look at that, it just is fundamentally wrong, because as we come up here, the shortest path to get to this new node would be actually to go through this one, not coming all the way up around and going down. So we'd rather get a shorter path, because we're trying to explore out, we're trying to find the shortest path to everything, right? So instead of having this new node be added directly to the closest, we're going to define a neighborhood set of nodes. So we find this node v new, and we're now going to, instead of just directly adding it to the closest node, we say, all right, let's find a neighborhood of nodes that are close to this new node. And we just drop down a ball of some radius, and we select all the nodes that are within that ball. And then we come through and we say, all right, well, what's the best node to connect this guy to given the rest of the tree? So we want to find the shortest path from PS to V new through this tree. So instead of connecting it to the closest node that we did, we connect it to the one that has the lowest cost within this radius that we're looking at. Okay, so let's walk through these steps. So we generate the new potential node v new. We've mentioned that. So instead of finding all the closest nodes in the tree, we find nodes within the neighborhood. And then we have this path cost. So this is the cost of the path from PS to V. So in other words, the big difference between the RRT extend and the RRT star extend is this path cost. Is that we're considering the path cost from the starting node to the new node instead of just the shortest length to get to a parent. Okay, there's one typo here. We're going to let V prime be the minimum, the arg minimum of the node of all of the potential path costs plus the path to get to the new node. So V is in N, and all of the V in the neighborhood set are already in the graph, right? And so this is the cost to the potential parent, and then the cost from the potential parent to V new. And so we say, hey, let's find let V prime be the arg min of this optimization. So we're just finding the best one. So that's what we did here. We just found the best one that has the lowest path cost instead of just the lowest distance. And right here it says the closest node in N to V new. That's not true. That's what RRT was doing. So that would be what we typically call as extend, and this would be called extend star. Excellent. So that's the difference between the RRT quote-unquote extend and the RRT star extend. So then we come through and we add the node. We add it to the node set, right? And then we add in our edge. So we have our new edge. Okay, and then we calculate our cost. So again, big difference here is we're just adding it to V prime instead of its closest one because we want to be locally optimal. The next thing we do is now that we've added in this V new, right? We have V new now in our graph. Now we want to look at the same neighborhood set and ask ourselves, is it better to go through V new to each node rather than its current parent? So we come in here and we could say, well, here's a bunch of potential edges that we could evaluate. Right? So would it be better to go through here? The answer is probably no on that one. So then we'll go through and we'll eliminate and say that's not a real potential. Would it be better to go here versus there? Maybe on that one. That's a definite possibility. We'd have to look at the distances there. But definitely, it is definitely better to go there than through the orange path to that node. Right? And so we can say, hey, while we're doing this, while we're adding in this node, let's optimally refine or locally refine our tree so that this new node is now could potentially be parents to nodes that already existed in the graph. So again, this is just saying exactly that. If they're for all the nodes in that neighborhood set, try to do the rerouting. If the cost to the path cost, right, to get to V new plus the distance cost from V new to V is less than what we currently, the previous path cost to V, so we have this over here on the left. This is a potential path cost. We have this potential path cost is less than the previous path cost. Then let's rewire the tree. We come in and we'd say, all right, we don't want that edge anymore. Instead, we want this edge. And I'm not sure, jury's still out on that one. But we definitely do not want that edge. Okay. So then we just rewired it and the graph would look the same except for it wouldn't have this edge in there. So we remove the edge to its parent and add an edge between V and V new. Okay, so here's some depictions of RRT versus RRT star. And this is from the original work that came out with RRT star by Karaman and Frizzoli. So if you see here, this is a standard RRT approach where you definitely see the jaggedness of these lines. We do not have straight lines connecting anything. So we have all these jagged lines going everywhere. But the results from RRT star is that as you're building your tree, you're building out basically straight lines everywhere. So this RRT star is trying to find the shortest path basically everywhere, which is really fantastic. So we're just, as the number of samples goes up as the number of samples increases, these lines get straighter and straighter. Okay, so that's obviously in an open environment. We definitely want that straight line. Here is in an obstacle-ridden environment. We see that now we get the straight line paths where the really interesting part is along these edges, right, where we see that we end up getting these straight lines to there and then we're getting straight lines off of them. And so you see that the path taken on the left with a standard RRT, very jagged and quite strange, compared with the right where we have a really nice straight line. Okay. So let's talk really quickly about some of these properties. RRT if we do our random sampling, will produce a dense sampling which is required actually for this asymptotic finding of a path. But we'll eventually get infinitely close to any point, and so that makes it probabilistically complete. So as the iterations go to infinity, the probability of finding a solution goes to 1. So we are probabilistically complete, which is fantastic, but we are optimal. We'll get the shortest path with probability 0. So we're not going to be finding that shortest path. Now this actually doesn't consider the path smoothing techniques that we discussed previously. This is just your standard RRT properties. RRT star properties, we are still dense, so we're going to be probabilistically complete, and we're going to be optimal with probability 1 as the number of iterations go to infinity. But it is important to note that the asymptotic convergence can be quite slow. So that with the more samples that you acquire, the less likely you are to improve the path. But we see here, again, a very different path for RRT versus RRT star. I was trying to find my green highlighter. All right. So RRT is going along this path. And it's a little bit harder to see it in this one, but the RRT star goes along this path, right? Oops. Okay. So we definitely ended up getting much better results. So I want to end with just a note on fillets. So fillets are a little bit bizarre in terms of or a little bit more difficult in terms of calculating the path length. These local refinements can be complicated a little bit by fillets because the local refinements might not produce the best result. So here's a very simple example where we have 2 paths that are going to R4, and say we could have potentially we have the tree, and for somehow it connects these two nodes with the exact same distance. So all we're doing is checking to see. We're checking to look at which one would be the best. Okay, so if we're going to x3, we would be adding in an additional cost of 1.9 if we go through x1. So that's better than going through x6, which adds a cost of 2. Right? So if we go to x3, then it costs 1.9 going through this one, and it costs 2 going through that one. Okay, but if we want to get to x4, we're going to add in this fillet actually cuts the corner, right? So it actually makes things a little bit cheaper. So the red route going straight through here would cost 1 plus 0.9 plus 1, so it would cost 2.9. The blue route would cost 1 plus 1/2 plus pi fourths plus 1/2, which is actually 2.785. So even though it's the longer path to take to get to x3, it's the shorter path to take to x4. So those local refinements start to cause us just a little bit of a headache. Okay, so we're going to talk about using RRT star and fillet-based methods. We're not going to talk too much about Dubins paths. So Dubins paths are shown here as the red, and you see that, let's just look at this one. Our Dubins paths end up having a harder time converging to a good path. And so you see that because we have to consider the orientation of the Dubins path, or the Dubins points, or the points in the Dubins path. And the other approaches that we'll look at for using fillets and also straight lines, they don't have this kind of wonky behavior that Dubins does. And you see this kind of wonky behavior all over the place when we're trying to solve paths using Dubins, that it has a hard time with that local refinement. Again, because the local refinement on a Dubins path, if we change the orientation slightly, we could be taking an entire different path to get there. So the local refinements have a hard time with the RRT star. Another thing to be looking at is that the These tables show the time in seconds it takes to get an initial solution, and this is the path lengths in meters after it has found that initial solution. So this is just the initial solution itself. And you see that Dubins takes a lot longer. We have arcs and straight lines actually are very comparable in terms of the number of how long it takes to get to those to the original goal. And in the maze world, it turned out that the arcs were actually faster using the arc fillet. This Bezier curve we're not going to talk about, but it does add the ability to add even more smoothness to our fillet. So the arc fillet does a immediate transition from zero curvature to a maximum curvature, where a Bezier fillet will be like a clothoid and have a smooth transition. Okay, so this is just another depiction to show why we won't care about Dubins paths. The x-axis here is the time to converge, or the time in seconds, and the y-axis is the solution length. I see that Dubins doesn't do super well, but the cool thing is that when we look at, we don't have the key there. But when we look at the arcs versus straight lines, we actually, we do. So here's our straight line and here's our arc. We end up getting really similar convergence results, which is really cool. So we'll jump in and we'll talk about arc-based fillets in a future lecture.